Hello everyone, my name is Saeed Moradi.
I'm Khaled Hassan.
Today I want to present our work called Version Analysis of Software Quality Indicators and Self-Admitted Technical Debt in Ethereum Smart Contracts with Ethstractor.
All right, so initially, we're going to start off with a little bit of a background on smart contracts. Smart contracts have two major characteristics that we're interested in. The first of which being immutability. This means that once a smart contract has been deployed to a blockchain or to a chain in general, the contents and behavior of a smart contract cannot be changed. And this stems from the immutability feature of a blockchain that is inherent to it. The second characteristic that we're interested in is the decentralization of smart contracts. A smart contract is not owned by a single. Instead, each node on the chain knows exactly what a contract does. And this creates a sense of transparency and trust such that any node can execute the smart contract without the need of a central authority or an intermediary to achieve the same output on every node. So these characteristics create a few challenges. The main challenge that we're interested in is the immutability, or it stems from the immutability characteristic. So if a vulnerable smart contract were to be deployed onto a chain, and that vulnerability were to be discovered post deployment, the smart contract wouldn't be able to be updated later on. And this same thing applies to technical debt. So if some deprecated piece of code were to be included in a smart contract and deployed onto the chain, it wouldn't be changeable later on. And so the only way to circumvent this is to actually redeploy a new version of the contract to a completely new address. However, doing so is not only challenging because you would have to potentially uh, um, migrate a lot of users to the new contract and along with their data, but also expensive because deploying a contract requires that the deployer pay gas fees. Depending on the contract, these gas fees can be high, and so because of this, it is imperative that contracts are checked and that they are any issues with them are detected early on before they are deployed onto the chain. In this work, we develop a tool called Ethstractor, which extracts versioned smart contracts from the Ethereum blockchain. Um, Using this tool, we created a comprehensive data set of versioned smart contracts from the main network of the Ethereum blockchain, and we used this data set in our subsequent analysis. We also examined the different code metrics such as source lines of code and maintainability index as we look at their effectiveness in indicating the presence of vulnerabilities in smart contracts. And we also investigate the self-admitted technical debt that is introduced into smart contracts and whether it's been paid off or not later on. So starting off with Ethstractor, this tool uses the Etherscan API for interacting with the Ethereum blockchain. We use the Etherscan API to circumvent the synchronization delays that would be associated with actually setting up a full node, a full Ethereum node. Using Ethstractor, we collected our data set, and this was done by analyzing the transactions that are associated with the deployer and some smart contract. These transactions are generally one of three types. So either a deployer directly deploys the smart contract, in which case we know this contract is deployed by this specific deployer. There's also a deployer using a deployer contract to deploy their target smart contract. This is generally known as keyless execution. And finally, the deployer or any other address for that matter interacting with a contract through a proxy contract. Using these three different types of transactions, we were able to link smart contracts to their deployers. And so this is a diagram showing the architecture of the Ethstractor tool. In our experiment, we had three instances of Ethstractor running. These three instances cycled through some Etherscan API keys because of some API limits. We fed smart contracts into Ethstractor through the Sanctuary dataset, which is publicly available. The Sanctuary dataset has a specific name format for each smart contract, which contains the deployer address and the smart contract address. And from there, we were able to link everything together and then query the Ethereum blockchain through Etherscan and collect our data and save it in our version dataset. This is a simple flowchart showing how Ethstractor would typically work. So it would have a contract from the Sanctuary dataset fed into Ethstractor. Ethstractor would then extract the deploy address from the name of the smart contract that is given by Sanctuary. It would then query Ethereum through Etherscan and find all the deployer transactions. And then it would go through the deploy transactions and find the creation transactions associated with the smart contract that we're interested in. So once Ethstractor would create the dataset or add new contracts to the dataset, it would also automatically commit the dataset to a GitHub repository in a similar manner as Sanctuary. And finally, like Ethstractor, we were able to amass a little over 159,000 unique contracts, which amounted to over 8,800 contracts per day. That's the rate of exploration that we achieved. This could either increase or decrease depending on the number of instances deployed on the machine that you're using.
After we collected our smart contracts to conduct this work, we finally decided to go about some code metrics that are being heavily and like popularly used in the scholarly articles and like in terms of software quality analysis. And of all those metrics, there are four metrics that are like really popular and like really used in like all senses. The first one is Makabe, or psychomatic complexity, which measures the number of decision points that you're having in a code snippet plus one. And the decision points that I'm talking about, they are usually called in different smart programming languages like while, for, if statements, and etc. And the second one is the source line of code, or a slog, which is basically the number of lines in a piece of code, absent this, the white spaces and comments. And the third one, which is called Halstead volume, is a measurement for detecting for calculating the size of a code with the number of operators and operands that we have in a piece of code. And finally, we have maintainability, which is a balanced calculation of all the aforementioned metrics that we are having here. And after we extracted our smart contracts and we finally could detect all those things in our smart contract codes, the slog, the hosted volume or Makabe, and maintainability, we ran some vulnerability correlation between code metrics and the vulnerability index that we found with our analysis metric called Slither. And finally, the correlation between the vulnerability and the code metrics that we found are stated in this table. And as we can see, the numbers are relatively low, which indicates that the correlation between vulnerability and code metrics are really weak and not very reliable, which means that you cannot use code metrics to detect or predict vulnerability in a smart contract, or it cannot be used for upgrading. It cannot be used for fixing bugs or predicting bugs in the future. And for versioning in a smart contract, we also, of the dataset that we found, that we collected, we could find some smart contracts that are having a lot of versions, so usually more than like 50 versions. We have like on the histogram on the left that shows all the smart contracts with more than 50 versions, and that these smart contracts, as we see, is like they are really rare. So of all the smart contracts, only 5 smart contract were having more than 50 versions. And on the right, we also see that most smart contracts only have one version. So as you see, like of all the smart contracts that we had, almost 80% of all the smart contracts only had one version, which means that the smart contracts are not usually upgraded or updated during time because of the cost that it will impose, and how difficult it is for developers to replace the smart contract with a new one.
All right. So when it comes to technical debt, there has been there has been a lot of work concerning technical debt in smart contracts. There hasn't been much done in regards to analyzing the evolution of the technical debt in a smart contract. Uh, Specifically here, we're talking about self-admitted technical debt, where developers recognize that they have technical debt in the code using the comments to identify it. Uh, Used keywords like to do, fixed, deprecated, and a bunch of other keywords to identify these comments that indicate that there is technical debt in the code block following it. The way we did this was we first collected our version data set, and then we extracted the comments from the very first version, the comments indicating that there is technical debt. And then we tracked whether these comments were removed later on. We also tracked whether new comments or new technical debt instances were added later on in later versions as well. Um, so Checking for technical debt is not very simple, because you also have to make sure that the if a comment is removed, it is also consistent with removing the actual code block that is recognized as technical debt. So you might have instances where the comment was removed but the technical debt itself wasn't, or where you have the technical debt being removed but the comment itself not being removed. We checked for these instances, and in our data set, we found no instances where inconsistent changes were made. Um, so this is a sample of the comments that we have in our data set. As you can see, all of them are generally have one of the keywords that I talked about before, either to do, fix, workaround, deprecated, etc. These are the results of our experiment. We found that normally technical debt persists over versions, so it's only removed in about 6.5% of the contracts, which means that if there is technical debt introduced into a contract, it's generally going to stay and not be removed. However, do note that we have a very low mean and median in initial debt, which means that in the first place, most of the time there is no initial self-admitted technical debt being introduced into the smart contract. However, if it is introduced, it's not going to be removed later on. So to wrap up, to summarize what we did, we created a tool called a Ethstractor to collect our version data set of smart contracts that have been deployed to Ethereum. We also found that code metrics are not reliable indicators of vulnerabilities in smart contracts, and that these vulnerabilities normally persist over different contract versions. We also found that technical debt is generally not removed from smart contracts as they evolve. In the future, we'd like to further analyze different types of vulnerabilities and their impacts on smart contracts, and would like to also try and use more sophisticated metrics for predicting the vulnerabilities. Finally, I'd like to thank everyone for their valuable time and for the opportunity to present our work, and I hope that our work contributes to more work being done in this field.
Thank you everybody for your attention. We appreciate it, and like we hope that we can work on this area of study further in the future to collaborate more in this area. Thank you.